Okay, so for today we're going to look at relative motion. So relative motion is just a kind of fancy way of saying how the speed of one thing compares to the speed of another. And we don't have to do too much with it at this stage. It's one of those things where once you've learnt about it, you'll recognise it in lots of everyday life situations. So let's take for the moment, we've got two cars and they're both travelling at the same speed along the road. So that's the two cars travelling on the road. Let's take them back to the beginning. So now let's consider two people, one in each car, obviously concentrating on the road, but happily smiling and waving to each other. And what happens when the vehicles are moving? So as far as the people are concerned, if those two vehicles are travelling at the same speed, when they look out the window to each other, then from their point of view, they stay in exactly the same positions. So relative to each other, they appear not to be moving. The person in the red car looks across and the person in the white car is always in the same place as they are relative to them. So even though the cars are both moving, relative to each other, they are not travelling. It's a bit like when you look out of the train window and you're going alongside and someone's walking alongside the platform as you're starting to set off, and they're walking along exactly the same speed as the train. If you ignore the background, the person you're looking at appears to be travelling with you at the same speed of the train, so they stay in the same place as you look out the window, and so therefore, compared to you, they appear not to be moving at all. And that's what this whole relative motion thing is all about. So back to our car example. So if the cars are travelling the same speed, then relative to each other, they appear not to be moving. As far as the person in each car is concerned, the other person stays in exactly the same place compared to them. And so, as far as compared to each other are concerned, or as far as the relative motion is concerned, they're not moving. Let's take the same situation, and this time let's see what happens with the cars travelling at slightly different speeds. So because they're travelling at different speeds, they both have a forward speed in the same direction, but there's a difference between them, and it's that difference between them that's the relative motion. So let's put some values on that. So if the top car was travelling at, say, 20 miles per hour, and the other car was travelling at 30 miles per hour, they're both travelling in the same direction. As far as the person in the slower car is concerned, the red car seems to go past them. So if the person in the slower car watches the red car go past, they appear to be going past with the difference between the speeds. So the relative speed of the red car compared to the white car would be 10 miles per hour forward, because it's going ahead or away from the white car with that difference in speed. So the relative motion is the difference between the two speeds, and because they're both going in the same direction, the relative motion of the red car compared to the white car is 10 miles an hour forwards or faster. If it was around, if the red car was watching the white car, then as far as the red car is concerned, the white car seems to be going away from them, so they'd be going 10 miles an hour slower, so their relative speed would be 10 miles an hour backwards. So as far as the red car is concerned, looking at the white car, they would see the white car going backwards at 10 miles an hour, even though they're actually not, they're just getting further behind the red car as the red car watches them out of the rearview mirror or the back window. So the trick with relative motion is to always think about which vehicle are you dealing with, or which person, and what is the other thing doing compared to you if you were in that position. So it's always one thing relative to the other, and you've got to think about, okay, is the other thing getting closer to me, in which case it has a relative motion towards me? Is it getting further away, in which case it would be backwards? And what's the difference between the two speeds? Another good way of thinking about it is put yourself in one of the positions and think, if I was stood still, what does it look like the other thing is doing? So we'll have a look at some more examples to help make a bit more sense of that. So let's think about two vehicles moving towards each other. So let's have the white vehicle can actually just be parked. And we'll have the other vehicle moving towards that car nice and slowly at 10 miles per hour. So what's happening is as this car moves towards that car, there's a difference in their speeds. That one's 0, not moving. This one is 10 miles an hour towards it. So their relative speed is 10 miles an hour, because that's the difference between the motion, and it's 10 miles an hour adding together or coming towards each other. If we were to change this one and have this one moving as well, let's say that one's moving 10 miles an hour that way. So the white car is going towards the red car at 10 miles an hour, and the red car is coming towards the white car at 10 miles an hour. Then, as far as they're concerned, as far as the white car looking at the red car is going to get closer to it twice as fast as before, because whereas before the white car wasn't moving and the red car was just moving towards it, now they're both moving towards each other. So even though each car is only going 10 miles an hour, the combined effect of those cars moving towards each other means that their relative speed is, add those together, their relative speed is 20 miles an hour. Because as one car moves towards the other one, they're both moving towards each other, and so it has double the effect. So there's actually only really two different sorts of situation you have to deal with when it comes to relative motion. You've got the situation where things are getting or moving towards each other, or you've got the situation where things are moving away from each other. Away from each other can be both vehicles going in the same direction but one not as fast as the other, or it can be both vehicles going in opposite directions. But if they're getting away from each other, then you use one set of rules. If they're moving towards each other, then you use a different set of rules. And I'm going to summarise those underneath in just a moment. So, if they're moving towards each other, in other words, if they're getting closer together, then the shortcut is you just add the speeds together. And then the other one is if they're moving away from each other, well, now it depends whether they're moving away from each other but they're going the same way, i.e. one's going faster than the other, or they're moving away from each other actually travelling in opposite directions. So if they're moving away from each other and they're travelling in the same direction, in other words, we've got one car going faster than the other car, then what we would do here is to work out the speed of the red car relative to the plain car. Then what you do is you take the speed of the car you're dealing with, so the speed of the red car is 60, and you subtract the speed of the plain car that's following it, which is 20, and that gives us a relative speed of 40 miles per hour. What that means is that the red car is getting 40 miles further away than from the white car every hour that's going on. So even though the car's driving at 60, compared to the white car, it's only getting away from it as if it was driving at 40. That's, of course, if they're moving away from each other but travelling in the same direction. If they are moving away from each other and travelling in opposite directions, let's give them the same speeds as before. So the white car is moving at 20 miles an hour and the red car is moving at 60 miles an hour. In this case, what we'd have to do is they're going to get further away from each other more quickly than before. So we would add the speeds together. So if the red car was to look out the rear window, they'd be getting away from the white car as though they're travelling at 80 miles an hour. And the white car, even though it's only travelling at 20, when it looks out the back and sees the red car getting away from it and it moving away from the red car, it also is travelling or appears to be getting away from that car at 80 miles an hour. So quite complicated, but let's just recap the main things. Whoops. If two vehicles are moving towards each other, add the speeds together. If they are moving away from each other, if they're going in the same direction, then you take the faster speed minus the slower speed, and that will give you the difference between them. But if they're travelling in opposite directions, then it's like the opposite of them coming together. So again, you add the speeds together, but this time this is the speed they're getting away from each other, not coming towards each other. So you don't actually have to do an awful lot with relative motion. There's a very, very small amount, and it's something that you do much more when you get into year 10. So it's not a problem if you're not completely happy with it at this stage. The key thing to remember at all times is if you were in one of the things that's moving and watching the other one, and you were pretending you were stood still, what does it look like the other thing is doing? So there's lots of examples of relative motion in real life. So if you're walking on the street and someone is walking alongside you but they're walking a bit faster, their relative motion would be the difference between their speed and your speed. So if you're walking at 1.5 miles an hour and they're walking at 2 miles an hour, compared to you, they seem to be moving at 0.5 mile an hour to get away from you. Relative motion is also interesting because right now on the surface of the Earth you might be sat still, but the Earth is spinning, so you are actually moving. So when you're sat still, your motion relative to the Earth is 0 because you're moving with the Earth, but as the Earth is spinning, your motion relative towards the centre of the Earth is around about 460 metres every second if you're on the equator, and that's just over 1,000 miles an hour. So right now, sat still, your speed is 0 relative to the Earth, but that point of the Earth that you're sat on is actually moving at just over 1,000 miles an hour. So that's where relative speed can be quite confusing sometimes, but also quite interesting, hopefully. Okay, so let's do a quick summary of a couple of examples. Two aircraft, one flying at 70 miles an hour and the other one flying at 85 miles per hour. So they're both going in the same direction, which means that their relative speeds, I'm just going to take the faster speed and subtract the slower speed, which means I have 85 miles per hour minus a 70, and that gives me a relative speed, i.e. the difference between them, of 15 miles per hour. So that's a relative speed, 50 miles an hour between the two planes. Let's take another example, two dogs, so they're pleased to see each other. So this dog is really happy to see the other dog, so runs towards him at 6 miles an hour. This dog's less keen, she kind of strolls towards the other dog at 2 miles an hour. Now they're coming towards each other, so that means we simply add the two speeds together. And that means we've got 6 plus 2, which gives us 8. So 8 miles an hour is the relative speed between these two dogs. That's how quickly they appear to be coming towards each other, because that's the combined effect of their 6 miles per hour and their 2 miles an hour in the same direction. Okay, so the vision guide's got a couple more examples, so have a look at that, and keep an eye out for situations when you're sort of around and about in life where you see or recognise relative motion happening. Okay, thanks very much.